Alright, in this video I will remind you how to sketch a graph of rational functions, functions that are made out of fractions of polynomials like these. We'll be talking about the points of discontinuity, any holes that we find, horizontal asymptotes, end behavior, all that stuff. And then if we have time, I will remind you how to sketch the graph of a piecewise function. So let's dive in and see what we can do. We always want to write the function in factored form, and the only thing I can do as far as writing this function in factored form is I'm looking at the denominator. It will be easier for me to sort of think about what's going on if I factor out this negative sign and pull it out in front of parentheses. So then I see I've got x minus 1. Alright, these are the same. Okay, that makes it easier to see that x cannot equal positive 1. Because if it did, I would get 0 in the denominator. So that is a point of discontinuity. Alright, this is going to be a vertical asymptote. So x cannot equal 1. This does not cancel out anything, so there won't be any holes. But let's go ahead and sketch the vertical asymptote because x cannot equal 1. So I'm just going to sketch this as a dotted line. Okay, alright, this is my vertical asymptote. Okay, so that means, maybe I'll write this off to the side, this is an infinite discontinuity. Okay, that's what you call it when you have an asymptote breaking up the graph like this. Now, as long as we're talking about asymptotes, will there be a horizontal asymptote? Whenever the degrees are the same in the numerator and the denominator, see how this has degree 1 and this is degree 1 as well? Whenever the degrees are the same, you will have a horizontal asymptote, and it's going to be formed by the coefficients of these terms. So in other words, the horizontal asymptote is going to be y equals, and then the coefficient here is 1, and the coefficient down here is negative 1. So it's going to be y equals 1 over negative 1. So in other words, y equals negative 1. So this is my, I wrote ha, that's horizontal asymptote at y equals negative 1. Okay, so let's go ahead and draw that in. So this is my horizontal asymptote right here. Okay, now let's see if we can find the zeros of the function, alright, the x-intercepts. So let's see, let me write this down. So the zeros of the function, you will find the zeros of the function by setting this function equal to 0. Okay, so I set the entire function equal to 0, and then that will give me the zeros of the function. The only way that this function is going to equal 0 is if the numerator equals 0. Alright, the denominator can't equal 0. So the only way the function is going to equal 0 is if x plus 3 is equal to 0. So that means x is equal to negative 3. So that means negative 3 is a 0 of the function. Or put another way, negative 3 comma 0 is an x-intercept. Okay, so let's graph that. So negative 3 comma 0, this is the x-intercept of the function. It's the one and only x-intercept of the function. Alright, now let's talk about the y-intercept. Alright, the y-intercept, let me just try to organize my work a little bit. you will get the y-intercept by plugging in 0 for x. Alright, and that's going to give you the y-intercept. So if I plug in 0 for x, alright, imagine I put a 0 here and a 0 here. Well, those terms are gone. That's just going to leave 3 over 1, or in other words, 3. So f at 0 is equal to 3. In other words, the y-intercept is 0, 3. Alright, so this is the y-intercept right here. So these points are enough to really show me that this branch of the function is going to look something like this. Alright, because I've got to pass through those points and approach these asymptotes. So that's going to look something like that. Alright, so I think I found all the stuff I'm supposed to find. Alright, I found the discontinuity, the holes. Well, there were no holes. Horizontal asymptote, intercepts. Okay, so I need another point, at least one point over here to help me draw the graph. So let's see what's happening at an x value of 2. Alright, I'm just going to substitute that point. Alright, let's find the point 2 comma what? What do we get? Alright, so let's see. So instead of plugging in 0, excuse me, imagine that we plug in 2. So I'm going to put a 2 here and here. So what's that going to give me? So that's going to give me 5 over, and then here I've got negative 2 plus 1, which is negative 1. So I've got 5 over negative 1, so that's going to be negative 5. So 2 comma negative 5 is another point on this graph. Alright, there's nothing special about it. I needed to see what's going on this side of the graph. So I just picked 2 because it's the first number I saw. So 2 comma negative 5 is on the graph. So I've got this point right here. Alright, and that's enough. I mean, we're just doing a rough sketch, so I know that I'm going to have a branch over here passing through that point and approaching the asymptotes. So that is enough of a graph, and the one thing I haven't done yet is end behavior, which I will do now. So let's see. Let's first the left. As x approaches negative infinity, alright, that's the left, f of x approaches negative 1. It's approaching the horizontal asymptote there. And as x approaches positive infinity, as we go to the right, the graph is also approaching negative 1. It's also approaching the horizontal asymptote. So there is the end behavior. Okay, that'll do it for problem number 13. I think I got all this stuff in there. Alright, let's do the same thing with number 14. I think it would be beneficial to rewrite this in factored form though. So let's see if we can just quickly factor. I'm assuming that it's all factorable. Let's see. So x squared can only factor as x and x. 3 has got to be 1 times 3. I need negative 4, so both of these are going to have to be negative. Alright, so we did that. X squared, that's going to be x and x. Again, 3, that's going to be 1 and 3. This time I need a positive 2 in the middle. So a negative 1 and a positive 3 here. Okay, let's start with the discontinuities. I'm looking at the denominators. I know that x cannot equal 1 because of the first factor. I know that x cannot equal negative 3 because of the second factor in the denominator. X cannot equal negative 3. Okay. Now, the x minus 1, we have the same factor in the numerator and the denominator. So that makes this a removable discontinuity. running out of space here. A removable discontinuity. Okay. In other words, this is a hole. Okay. Because I'm graphing this, it's not enough for me just to know where what the x value is. This is going to be a hole, so it's going to have an x value and a y value. So the hole has an x value of 1. Okay, but I need to know what's the y value of the hole. Now, to figure out the y value of the hole, take the x value and plug it into the remaining portion of the function. So after I remove the discontinuity, the rest of the function is x minus 3 over x plus 3. So if I substitute 1 in for x, alright, that would give me 1 minus 3 over 1 plus 4. Okay, so that would be negative 2 over 5. What is this as a decimal? I mean, you know, so this is negative 2/5, 1 comma negative 2/5. 2/5 is 0.4, so this is the same thing as 1 comma negative 0.4. So there's a hole here, a removable discontinuity. So let's graph that. So 1 comma negative 0.4 would be like here. Alright, so I'm going to put an open circle there because that's a hole. Now, what about this other discontinuity? X cannot equal negative 3. Now this one was not removable. It's still there. So that means that this is a vertical asymptote. This is going to be an infinite discontinuity. Okay, in other words, a vertical asymptote. So I'm going to have a vertical asymptote at negative 3. Alright, vertical asymptote. So I'm going to go over to negative 3 and sketch this vertical asymptote. Okay, my infinite discontinuity. Alright, as long as I'm talking about asymptotes, let's talk about horizontal asymptote. Alright, I'm going to just put HA for horizontal asymptotes. Alright, I've already dealt with the hole, the removable discontinuity. So for the rest of the problem, I'm going to focus my eyes on this version of the function. The degrees are the same. They're both linear. Whenever that happens, the horizontal asymptote is going to be y equals, and then you wind up using the coefficients, which is 1 over 1. So y equals 1 is a horizontal asymptote. Okay, so I'm going to go ahead and put in the horizontal asymptote at y equals 1, like that. Alright, now it's time to find the zeros and the y-intercept. Okay, so let's find the zeros and let's find the y-intercept. Okay, when I want to find the zeros, I set f of x equal to 0. When I want to find the y-intercept, I substitute 0 in for x, and then that gives me the y-intercept. Okay, so let's do that. And again, I might as well use the simpler version of the function. I already know there's a hole, so I can go ahead and remove that discontinuity. So I'm setting this equal to 0 to find the zeros. The only way this fraction is going to equal 0 is if the numerator equals 0. The denominator can't equal 0. So the only way is if x minus 3 equals 0. That's the only way. So if x minus 3 equals 0, then that means x equals 3. That's a 0 of the function, the 0. In other words, I have an x-intercept at 3 comma 0. Okay, might as well graph that. Okay, so 3 comma 0, that's right here. So so there's my x-intercept. Now let's go find the y-intercept. So for the y-intercept, I substitute 0 in for x. Well, if I put 0 in here and here, that's just going to leave -3 over +3. So that's -1. So f at 0 is equal to -1. In other words, my y-intercept is 0, comma, -1. Let's graph that. Alright, 0, comma, -1. Here's my y-intercept right here. So basically, even though one of them is an open circle, I have 3 points that I can use. I know these are asymptotes. So I can definitely go ahead and sketch this graph man. This graph, I can sketch this branch anyway. Okay, let me be careful not to violate this open circle. Alright, and I'm approaching the asymptotes. So there's that branch. I need at least 1 point over here to kind of see what's going on. So I'm just going to do -4. Let's just see what's happening at -4. Okay, and again, I'm going to use this version of the function. So let's find what's happening at an x value of -4. Like -4 comma what? If I substitute in -4, alright, let me just get this stuff out of the way for a second. If I substitute in -4, then that's going to give me -4 minus 3 over -4 plus 3. So that's going to be -7 over -1. So that's going to be 7. So -4 comma 7 is a point on the graph. Okay, so let's plot that. So -4 comma 7 would be right here. So this is a point on the graph. Alright, that's enough. So I'm going to go ahead and draw this branch. Alright, because I know it's got to go through here and it's got to come down and approach the asymptote on either end. Alright, this is just a rough sketch. This is good enough. So really that's it. We've done it. Let me squeeze in the end behavior. So on the left, as x approaches -infinity, f of x approaches. On the left, the function is approaching 1, the horizontal asymptote. Alright, as x approaches +infinity, f of x approaches 1 again. Alright, again it's approaching the horizontal asymptote. Alright, so there's your end behavior. Okay, so that is it for number 14. Alright, that took a little bit too long to graph the rational functions, so I'm going to have to show you how to draw the graph of a piecewise function on the next video. We'll do these two functions on one more video. Hopefully it won't take that long. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.